main speaker in this afternoon session is Arie Gurfinkel. Arie got his PhD from the University of Toronto in 2007 and then has been at CNU for quite some time. And just recently, in September this year, he moved back to Canada and now is a professor at the University of Waterloo. So Arie is known for his work on verification, reasoning about programs. In particular, he has built this verification framework, SeaHorn, which is a very interesting model checker for C, C++, and programs via LLVM. So welcome and go ahead.
Thank you, and thank you, Peter and Martin, for Okay, and so first let me sort of get the starting point. So what I'm talking about is automated software analysis, and from a very high level of abstraction, what I work is in this box. It takes a program as input, sometimes a specification, sometimes the specification is implicit, like it should not crash, and it comes back and says either correct or incorrect. Okay, that's sort of my world. And then it's built around two approaches. So my work is influenced by two things. On one hand, there's model checking. And on the other hand, there's abstract interpretation. For model checking, I have a desire of having an algorithm that always says yes or no. So it always either gives me, says that the property is satisfied, or gives me a counter example, or dies trying. So I never want my tool to return an answer and say, I've tried my best, I give up. And then from abstract interpretation, I want the techniques to apply to real software. So not just some models of software, not something that the user constructs at small and finite state, but real software as it is written. And of course, this makes this problem really, really challenging. So program analysis is challenging by itself, but if you also say, I want always an answer, and I want a tool that runs on a real program, that becomes undecidable. Right? And so we know that we know this from Alan Turing, that this problem is undecidable. We still want to do something about it. But one other interesting thing that's less widely known is that Turing also was thinking about this problem in a more general sense of what does it mean for a program to be correct, and how should we talk about it. And he had this paper in 1949 called Checking a Large Routine. It wasn't really widely known, and until maybe 1984, it was sort of hidden in some archive. And in 1984, a group of people found it and rewritten it for with a current presentation to explain what Turing really meant. But what he was wondering about in this paper is what does it mean for something to be correct? And as an example, he took a program of a factorial, so a program that computes a factorial. He didn't have a programming language at that time, so he said, okay, we'll just describe it using this block diagram. And then he said, well, what would convince me that this program, in fact, computes a factorial? And what he was proposing was an intuition that this is similar to sort of inductive proofs. It's hard to find an inductive hypothesis, but easy to check. He said the programmer or somebody has to provide this annotation, so this is things over here, in such a way that the annotations imply that the program is correct. So this is goes through animation. So this is the annotation that says at the output of the program, we have n factorial. And in such a way that from any pair of annotations, you can know that they're correct relative to each box that they label. Right? And of course, we all know this now as a Floyd-Hoare proof method, and these annotations are known as inductive invariants. But in fact, Turing was proposing something very, very similar way before it was rediscovered again. Well, but from perspective of my talk, what automated verification is to me is finding these annotations automatically and verifying them automatically. So this is what we're going to do. I'm going to divide automated verification, again, itself into sort of two parts. There's one part I'll call deductive verification, and it says, let the user specify the problem really well, basically give me as much as possible of all of the annotations that I need, and I'm going to automatically check that these annotations are correct. And then I live more in this algorithmic verification world, where I will say, let's make the problem harder. The user just tells us what they really want, like no buffer overflows, and we're going to synthesize the certificate that we need and check it or we're going to construct a counterexample. So this is sort of the starting point. And for the last several years, we wanted to look a different way at this algorithmic verification problem. So the traditional way to do it is you just build an algorithm. You build an algorithm that does something like an abstract interpreter, and then you argue that it is correct, and you have an algorithm. You want to build a new algorithm, you build it again, you argue it's correct, and so on and so on. And what we wanted to do is build something that we call algorithmic logic-based verification that separates this process into 3 steps. We have the first step where we have a program and specification. We're then going to convert this into a verification condition in a suitable logic. And there's a question which logic we need. And then we're going to give it to a decision procedure that's going to do the actual algorithmic reasoning, and it will say yes or no. So it's logic-based because we have logic in here, and it's algorithmic because everything is done by a decision procedure. Of course, this covers a large space of possible verification methods, and our focus here is applying this exactly in cases that are typically done by a model checker or a static analysis. And so what that means in terms of these boxes is that for specification, we focus on safety properties. So things like assertions, things that I can prove to you that they don't hold by giving you a counterexample. And then for logic, we need some sort of logic that is strong enough to express that we need an inductive invariant. We don't going to have an inductive invariant to begin with in a verification condition, but we'll say that the decision procedure has to find one. And this logic is the one that we're using is called constraint horn clauses. And towards maybe the middle of a talk, I'm going to give you more details on what it is. And then the decision procedure is something that we build on our own based on SMT solvers. And the decision procedure is called spacer. Okay, so what I'm going to do it first is I'm going to talk about SeaHorn, which is an implementation of this kind of framework for C and C++ based on LLVM. And then I'll talk about the constraint horn clauses and the decision procedure in it. So just to give you a quick overview of a tool. So a tool is called SeaHorn. There's this beautiful picture in the background that you don't see because it's all black. But it's a beautiful picture of C, and it's wonderful. If you really want to see it, you can go to this website, and you can see the picture in much better colors, and you can also download the tool or look at the source code if you want. The main developers is myself, together with Temek Hasai, who's now at NASA and CMU Silicon Valley, and Jorge Navas, who used to be at NASA until, I think, last week, and is now at SRI. From the user perspective, the tool is very simple. All that you do as a user is you give a C program of some kind. You indicate where you want, what you want to verify by assertion. You run the tool, and immediately you get an answer, true or false. Okay? Of course, because the problem is undecidable, sometimes you don't get neither true or false, but you're never going to get an answer that's the tool that is incorrect, and there are lots of assumptions. And the tool will never give up. It will always continue to try and prove whatever you're asking it to prove. I'm going to do a demo of it, so hopefully it'll be clear what it can do. Now, in terms of our philosophy, and this is to explain sort of what are we trying to achieve, because we're trying to do 2 things. On one hand, we want to build a state-of-the-art software model checker, which means we don't just want to show that you can use this logic framework to do something. We want it to be the best tool around, and I'll try to convince you that we are getting there. And at the same time, we also want it to be something that's useful not just to the users of verification technology, but also to the research community. So we're trying to develop it in such a way that it's somewhat modular, that you can pick up various components, and if you have an idea of what to do something in verification, you don't have to rebuild the whole infrastructure from scratch, but you can plug into a framework and try and do it. And several people have done that and seem to have positive experience so far. Now, the second thing is that the second part of our philosophy is we want to stand on shoulders of giants. In particular, we build our tool inside LLVM framework, and we work very, very hard to figure out how can we achieve what we need using existing tools and techniques. So for example, in order to generate verification conditions, you often need to put a program in a special form that makes it easier. In our case, we figured out that this form is very close to a single static assignment, and so we're using a single static assignment algorithm of LLVM for that. And often you have to be very creative. You have to think about, here's my problem, This is how I can convert it to reduce and sum to some existing problem, use an existing solution, and recover my solution. And so we use a lot of LLVM. We use a lot of components. We use them out of the box. We modify them, and we use them in different creative ways. And of course, for verification itself, we're trying to get the verification, the algorithmic part of it, to be completely inside the logic-based decision procedure. And so it's completely hidden in that part of the tool. So I don't have this clicker working. So this is the architecture. Yeah, I know, I keep forgetting that I did not plug it. I know it's okay, so this is the architecture. So everything starts here with C and C++ code and ends up here with yes or no answer. So the front end is based on LLVM. It takes C and C++ code and produces LLVM intermediate representation called the bit code. What happens in here is we use a lot of LLVM optimizations, but we change them or use a different pipeline so that to make the program more verifiable as opposed to run faster or use less memory. We do the obvious things like devirtualizing virtual function calls, property instrumentations for properties like buffer overflows, so things that are easy to say but hard to turn into assertions. And then we also lift all of the assertions to the main level. So at the end of this process, every assertion in the program is always inside the main function. And we have a technique of how to do it without blowing up the program too much. And then after that, for the front end, we get this intermediate representation, the bit code. And in this case, we disambiguate the heap, break heap into different parts, and generate the verification conditions. And so here you'll see lots of different options for different verification conditions that you can generate. This is the part of a tool that does various forms of abstractions, tries different proof techniques, and decides how it's going to attack the problem. And then finally, the output of it is this verification condition as in the logic of Horn clauses. And then it goes to the decision engine. And I'll talk about Spacer. That's what I'll talk about today. We also have an abstract interpreter called CROB, and then various other engines being constructed. So what I want to do is I want to give you a short demo of how it looks like. So let's see if this works. I'm going to use a very simple, small program. The tool runs on programs which are more than that many lines, but we're just going to use very small examples. And so I just want to illustrate just how it works. So we're going to start with a simple program that has this function main. We're going to use an assert in here to indicate what is a bad state, what is the behavior we don't want. We're going to use functions without bodies, like this function nd in here, to represent an arbitrary function. So this is, we're calling some function. We don't have the body of it. It will return some value. It will be type correct, but that's all that we know about it. And we're going to use a function assume to restrict those values. So you can think of an assume as a function that gets into an infinite loop if its condition is false, and otherwise it does nothing. So this whole block of code means that we start with some number n, and it gets some value from the function nd. Then we only continue if n is positive. We get another value k. We only continue if k happens to be bigger than n. And then we set j to 0, and we start doing something in a loop, and then we get to this point, and we check whether k is 0 or not. Okay. So the first question before I run the tool is, what do you think about this program? Should it fail the assertion or not? So the trick is, of course, to look at the bottom of the screen, because if you look right here, it says true. So probably it's going to be an example that will say true. So let's run it. So to run SeaHorn, we have a command called C. Let me move it to the top of the screen. Call a command called C. And the way you think about it like a git command. So you have a command and subcommand. So C is the main command. And the subcommand that we're going to use is called proof. And we're going to give it our program, press a button, and after, let me add another option just so that it's easier to read. And after a short time, we're going to get an answer true right here. Just to show you what happened so far. So I told you that there's this different pipeline of things that's happening. And so the command line is difficult to read, but if you look at sort of keywords. So we run the Clang compiler, just a standard Clang compiler to compile the program. We then do some pre-processing to massage it a little bit. We then do lift the assertions up, again using our pre-processing step. We then run Clang LLVM optimizations, but slightly modified pipeline. That's why it's C-opt instead of the normal opt. And then eventually it goes into a verifier that generates a verification condition and verifies it. We can also look at what the solution is. So we can ask it to show the invariants, and then it will print something like this. The invariants can be good enough to check that whether they're true or not, but they're fairly hard to read, in part because this is how the solver wants to read them, so they're not easy to read for humans, in part because they're done on the transformed program and converted by a compiler. So there's funny names, the _0, k, and j.0, and things like that. This is a compiler introduced through various optimizations. We could ask it to run the program without optimizations and without our pre-processing. And for small programs, this will work just fine. And so here we'll get the result that's closer to our original program. So we have something about assert, which was a function that we introduced that would call an error function if something is wrong. And for the assert, we discovered the summary, that it will raise an error flag if the assertion fails. And then for the main program, we discovered that this is how the main variables are related, and then that the end case bigger or equal than 1, and therefore the error flag is going to be false. So now let's look at another example. Okay. So it's more or less the same program, but the only thing that I've done is I've changed the assumptions. So now we assume that k is bigger or equal than 2, and we don't make any assumptions on it. Right? And of course, I have to ask you, what do you think? Will this program fail or not? Fail. And how do you know? Exactly, because it says false. That's the fastest verifier ever, because you just look at the name of the code and you know. OK, so we're going to run the same thing. And of course, the result is going to be false, as we expected. And it was very quick, because I prepared it for you. So I picked a small example that actually works. But what do we do with this now? Right, so this is one of the usual problems with any kind of analyzer. If it tells me that there is a problem, I want it to explain to me in a way that I can understand as a developer, what is this problem? And so the nice thing about model checkers is that they usually produce counterexamples. But usually a counterexample is just more text that says, this is how the model checker thinks you think works. And what we really want is we want to produce an actual execution, not just the text. And so we have an ability to generate a counterexample harness. So I'm going to run it again and use this option counterexample. And it will generate a LLVM representation of the harness, of everything that I need to do to drive this program into an error. Okay, so this is going to be some LLVM code. You don't have to read and understand it. I'll just show you what's happening with it, and I'll show you a few slides on that. But now what we can do is we can take our original program, that's false, and compile it together with the harness. Option. Okay. So what happened is that, what happened in this option is I've taken the original C program and I linked it together with a harness, and I got a binary called out. Okay? So now if I run this binary, it will tell me that the error is executed. It's right there in the bottom. So let me again. If I run it, it tells me that the error is executed. Moreover, if I, for example, go into GDB, into LLDB actually in this case, and I'll say that I want to break in main, and I run, then we're going to get to this place. So the program is running, and as I keep stepping, something is happening. I can get the value of n, I can get the value of k, and so on. Of course, if I'm a programmer and I don't really like spending too much time in the debugger, I can go inside my program and start changing it to see how it's going to behave under different conditions or produce various outputs. For example, we can go here and print the value of all the variables. So let's say we want to print n, a, and j. Right? And we can recompile the program, generate a test case, run it again, and so now we see the values being printed. So the reason why we have, again, let me run it at the top of the screen. So the reason that we get into an error is that we start with n equals 3, k equals 2, and then we get to the bad state. So that's it for a short demo. Unless you have any other questions or suggestions for it. Okay, so let me go back to the slides. So this is how SeaHorn works in practice. So the idea is, as I said, to produce an output in all cases and to produce a useful output. So either a certificate that you can at least examine or a counterexample that you could really use. Let me tell you a little bit about the counterexample stuff, because this is sort of the latest thing that we're doing, and we're really excited to be able to do it. So I showed you how it works on simple examples. And of course, the basic flow is very obvious. You would run a model checker first, and then you use the model checker run somehow to guide the symbolic execution engine to actually execute the program. And from that, you somehow collect the values that you need and package them in order to be linked into the program. Of course, there's lots of challenges in all of the steps. Well, we need to have a model checker that can actually find the counterexamples that's at a good enough level. We need traces from it to have enough detail so that we can guide symbolic execution. We have to actually guide symbolic execution somehow. And then after all of this, we have to actually generate this executable harness. And all of those things are easy on simple programs. And once you get into details, they become hard. So just to give you a flavor of what a harness looks like. So this is what we are generating. So say this is the input program that we verified. And this is the harness that we would want to get. So in the input program, we'll see that if we call this getInput function twice, and it gives us this magic values, then we're going to get into an error. And this is what the model checker knows. And then what we do from this is we construct a body of this getInput function that basically keeps track of how many times it was called and returns these values at this time. And the interesting thing, this by itself is really simple, but the interesting thing about it is that because the compilers treat external function calls very conservatively, we know that they always preserve chains of calls, independently of how many optimizations you've applied. Which means if we collect this information of how many times a function called on some version of a program that's heavily modified and optimized and inline, that's going to be still the same calls, the same number, in the same order in the original program. So we can generate this harness over something that, say, the user will never understand because it's highly modified and targeting towards verification. But we can use it with the original program, and it will, most times, will work just fine. Now, the things the place where this gets into a problem is once we start looking at real programs that use memory. And what we see there that it's very common in model checking environments to have external functions that return pointers and not just integers. And then we have a problem that, especially in low-level embedded code, where tools like this would work, there's often a dependency not just on pointers, but also on pointer values. So here's an example of a code from a Linux device driver verification project. And so they use this function LDV pointer to create pointers into anywhere. So this could be pointers into an existing data structure, so pointers for some new data structure. But then there's even comparison between pointers and actual raw values. Right? And this comes from a model of the Linux kernel that reserves a particular block of memory and the Linux kernel is using the value of a pointer to decide whether it's a flag of some kind or a real address. And then in the verification environment, they decided to set this number to 2012. And so now when we have to generate a real counter example, we have to take this into account. So the layout of the structures and actual values of pointers and relative values of pointers. Then you have to deal with things like an expectation that these functions may return a pointer to a completely allocated, well-formed data structure. So you may have a function like make new object, and the expectation is that it returns a well-formed object, and that somehow causes you to get into a bad state eventually. What we do for this is developed an environment where if we cannot generate a complete model of what the program wants, then at least we can simulate what the program needs. And the way we do it is we separate the program and memory. And because we are in a compiler, we don't need to interpret the program. We can just modify it immediately. And we start trapping its accesses. And so if we have a memory access that goes to an internal memory is memory that's allocated explicitly by the program using malloc or something like this, then we just map it to an actual hardware memory and let the program talk to that memory. But if we see an access that goes to external memory, which is a pointer returned by the function, by an external function that we know has not yet been allocated, then we start redirecting it into memory, but this purple arrow indicates that we do something to it in order to ensure that this memory access succeeds. So if it's a new access to a new memory region, then we just allocate some memory and then let the program use that memory. And if we happen to guess wrong what's the amount of memory we allocated, and the program is trying to get out and write to virtual external memory that's not mapped to any memory, then we simply ignore all the stores and return some default value for the load. Right? So this at least simulates the program enough for the user so that they can still run it in a debugger and at least see that if there is a counter example, then it is actually in there, it's actually executable, but maybe only with this funny memory model. So this is all that I wanted to tell you about SeaHorn. I want to now switch to the other part, sort of go under the covers and see how it actually works. So what's the actual logic into it? And for that, before we can go deeper into the details, let's first look at what is the problem that we're trying to solve, and let's try and state it in logical terms to see what is the statement that we need. So at the very core of it, what we're trying to do is we're trying to prove whether in some graph, a graph of program states, an initial state can reach a bad state. And so we have two possible things. It's possible that we have a counter example, in which case we have to find a path that goes from initial state to a bad state. And it's possible, if there is no counter example, then we should be able to find an inductive invariant, which is a set of states, something that's bigger than init, and closed under a program step. Right? And closed under a program step means that if we pick any state inside the invariant, and if we look at any of its successors where you can only go inside. Right? So if we go somewhere, it'll be inside. And if we go somewhere else, it will always be inside. There's no transitions outside. That's how we know that the program is safe. Try to express this in logical terms. Well, then it looks like we're solving these two problems. We're given a reachability problem as an input. It has a set of initial states, a set of bad states, and a transition relation. And we can assume that those are represented by some formula. And then we know that the program is unsafe if there is some n for which this formula becomes satisfiable, right? Where this formula is built by taking a transition relation, making n copies of it, stitching them together, attaching an initial state on one end and a bad state on the other end. And we know that it's safe if it has an inductive invariant, but logically it means that there is some formula inf that contains init and that is closed under an application of TR and does not contain any bad states. If we now look at this from the perspective of logic, the problem that we're trying to solve is really whether this formula is satisfiable in a sense of whether there exists something that we can plug for this unknown inf such that it becomes true. And if you look at this a little bit more and you look at various logics, you'll see that this is the logic of horn clauses. This is the same logic that, say, underlines prolog or data log, where we have this rules that tells us how can we go from one place to another, and we have these unknowns that we need to find. To look at it a little more formally, then the logic that we need is the logic of constrained horn clauses that consists, it's a fragment of first order logic that consists of the following clauses or rules. We have this phi, which is a set of background constraints. Technically, they could be any constraints, and for all of my work, they're usually something that includes part of arithmetic and a part of arrays to represent heap, and maybe sometimes bit vectors to represent low-level bit manipulations. And then this unknown predicates. And the intuition of each of this formula, it's sort of each predicate represents either a program location or part of an invariant. And the rule says if I'm in certain locations and under certain conditions, and I have a formula phi that and the side condition is true, then I get to go into H. And it's easiest to just look at an example of how we can encode a verification condition in this logic. So here on the left, I have a program. It's written in a C-like language, and the star here represents a non-deterministic choice. So here we have this program that's represented by a control flow graph. That's how a compiler sees this program. We have basic blocks. Each one has a different label, and then the statements correspond to what the program is doing. And this is how the verification condition looks for this program. So what we, if you look, each line of this corresponds effectively to one edge in the control flow graph. Each predicate pi corresponds to location li, and intuitively it tells you it represents the set of all states that are reachable by the program at this location. And now if we look at this, we can interpret it in two ways. So one way is we can interpret it just as a set of rules, where if we have a predicate that we know is true, then we can go and plug it in the rule on the right-hand side and see if the side condition is true, and then create another true predicate. So for example, here, P0 has no side condition, so it can be true. Because P0 is true, under a condition that x is 1, y is 0, P1 becomes true. So that means P1, 1, 0 is true. Because P1, 1, 0 is true, P2, 1, 0 is true. Because P2, 1, 0 is true, under condition x prime is x plus y prime is y plus 1, P1 becomes true with the appropriate arguments, and so on. So you could see that sort of each step in this rules corresponds to an execution of the program. So in some sense, this logical formula captures what the program is doing. And another way to look at it is we could try and guess how to satisfy this formula, how to make it true. In which case, we would have to guess for values for these predicates, so just tuples that we put in them, and they would have to satisfy those rules. Right, so here we'll see that we have this predicate P error that has to go into false, which means the only solution for it has to be false. From here, we're going to get that P3 has to be such that it doesn't satisfy this condition, so all the tuples where x is less than y have to be excluded from it, because otherwise P4 cannot be false, or P error cannot be false, and so on and so on. So this is the logic that we're going to be solving. So the tool that we use to solve it, this is a decision procedure that we've developed. It's called Spacer, and it tries to use the power of SMT solvers, but to solve not just, say, a bounded verification problem, or just to decide whether something is true or false, but tries to solve the horn clause problem, which is to guess the value of the uninterpreted predicate such that the formula becomes true or false. It itself is an open source tool. It's currently a fork of Z3, just because it's hard to integrate with Z3 in other ways. In fact, it's just an engine inside Z3. It's publicly available from here. And some of the nice features about it, it supports both linear and nonlinear horn clauses. So nonlinear is the ones that have more than one unknowns on the left-hand side. And they're useful in order to construct modular proofs. And then it supports a number of theories, and in particular, arrays and arithmetic. So to give you an idea of how it works, so I'm first going to go from a very, very high level, and then I'm going to try and animate through an algorithm to give you an idea of how it works. So the basic principle of the algorithm is to do verification by evolving approximations. The idea is that while we can't verify the whole program, that's undecidable, we are often quite capable of verifying a finite abstraction of this program. And sometimes from a finite abstraction of this program, we can guess how the proof would go for the whole program. And so this is, we basically get into this loop. We start with a program that we want to verify, and because we can't verify an arbitrary program, we approximate it in some way. And in particular, we bound everything that we can bound. So think if a program has loops, that we're going to bound the number of steps of each loop. Now this program becomes decidable, so we use some kind of a solver to find a solution for it. And we don't just get a solution yes or no, we're solving it as a constrained horn problem, so we're going to get the solution to our predicates, which is basically will be a horse-style proof for why this bounded version of a program is correct. We're then going to take those annotations that we got for the bounded program and then check whether they happen to be an actual certificate for the whole program. If it is, we're done. If not, then there's some executions that are not covered by that certificate. So that will tell us where we need to approximate more. We approximate more, solve it again, get new certificate, check it again, and if this doesn't work, we continue going on and on and on. Okay? So it's a very simple idea and principle, and the difficulty in making it work is to figure out how to make all of the steps efficiently. Because if you're just going to do individual solvers and going to separately solve each of those individual problems, then the further you go, the harder it becomes, and it quickly becomes too difficult for the tools. So the trick is how to do all of the solving, but in some way that you share as much of the information as you can. The algorithm that I'm going to show you here, in particular, is based on an extension of an algorithm from hardware model checking called IC3 that was developed by Aaron Bradley a few years ago. And what we're bringing to this algorithm, so this is just was a few papers, a few historical references on the algorithm. But what we're bringing to it is described in the 3 papers, which extend the algorithm first to theories, and second to ability to deal with nonlinear horn clauses, the ability to have more than one unknown. So give you the overview of an algorithm. It's divided into these 2 components. So there's this main loop, and 2 things happen in the middle. We have a call to a function called makeSafe, and this is the function that does this bounded verification. It picks an approximation and verifies this. And then we have a call to a function PDR-push, which tries to check whether the result is inductive, and actually tries to make it as inductive as possible, trying to use the annotations as much as possible. And then if it succeeds, we return and we say that the program is safe. And if it doesn't succeed, we increment our bound and we go back to the top. So what I'm going to do is I'm going to animate through a run of PDR make safe and a run of PDR make push. So this is our starting point in make safe. So what you're seeing in the picture is as follows. This gray thing at here, this is our initial bed state. Think about it as an assignment of values to variables, something like x is 1, y is 0. This blue things represents an unrolling of our transition system. So in this case, it means that we have 1, 2, 3, 4, 5 steps of a transition system. And here in the bottom, we're going to see the fact that the algorithm learns about it as it progresses. So we start with the bad state, and we're trying to prove that this program is safe in 5 steps. Alternatively, we're trying to prove that there is no path if we go back from this state towards the initial state. We do each step of this algorithm using an SMT solver. So we go to a solver and we ask whether our transition system can make one step and get to the state. And let's assume that the answer is yes. Right, and so we're going to get another gray state. And now we know that we can get from this state to a bad state. We're going to do this again. And so maybe we get a state x equals 3, y equals 0. And we're going to do this again and again and again. And of course, if we can do it all the way to the initial state, that means we found a counterexample. So at some point, we're going to get stuck. We're going to ask a solver if there is a predecessor, and the answer will be no. But at this point, we know something really important. We actually know that the program cannot get to the state, x equals 3, y equals 0, in 3 steps of the algorithm. So we can remember this fact, and I'm going to call this purple thing a lemma, and it's going to be a formula that explains what we know about the program at this point in time. So we know that x is not 3 and y is not 0. And if we're a little bit smart, and if we go through an SMT solver and see what reasoning it has done, we may be able to generalize it into something more, and maybe if we're lucky, we can find out actually what we know here is that at this point in the program, x is less than y, and that's in conflict with x equals 3, y equals 0, and this explains why we cannot proceed and build this counterexample. We learned one fact. And if we do this reasoning carefully, we can also say this fact had to be true in all of the previous steps in the program, because if it wasn't true, then when we were solving this problem with a smaller bound, we would have found the same bad state. But now, if we couldn't discharge it, then we would have gotten to the initial state, and we would have found a counterexample before. So every time we add a fact, we're going to add it all the way in the previous states. And then the algorithm continues to do exactly the same thing again. So now this state doesn't have a predecessor, so we have to go back here and check whether this state has another predecessor. Go back, we find another state, and then maybe it has another state. But again, this cannot continue like that forever, because in this example, we're not going to get a counterexample. So at some point, it's going to stop, and we're going to learn another lemma. Right? So now this lemma is a negation of this state, and maybe a generalized version of it. And then this proceeds in the following way. So now we come back here. We try to find a predecessor, and if it doesn't exist, we get another lemma. Then we'll come here, ask for another predecessor. And if it doesn't exist, we get another lemma. Come here, ask for a predecessor, and if it doesn't exist, we get another lemma. Okay? And this is how reasoning proceeds. Once we get to this point, what do we know? Well, first we know there are no counterexamples of 5 steps. Why? Because we started with a bad state. We tried to go back in all possible ways, and all of them got blocked. So there is no counterexample of 5 steps. We also know that we have a proof of why there is no counterexample. And the proof goes like this. It says, this is everything in here is true in the initial state. And if this is true, then this is true in the next step. And if this is true, then this is true in the next step. And eventually this is true in the last step, and that contradicts the bad state. So we have a Hoare-style proof explaining why this bounded program is correct. Okay? And so now we move to the pushing phase. And in the pushing phase, we just look at these things as possible annotations. And we're just trying, using again an SMT solver, to check whether any of the annotation is true somewhere in the future. And to do this, we'll pick each annotation, say this one, and we check if it's true in the initial state, and we make one step of a transition relation, is it still true here? Right? So this is a statement about one step of a program, so we can give it to an SMT solver to check for us. And if it will be true, we'll move the lemma over there. And if it's false, we just move to the next lemma. Imagine that we go and do it for all of those lemmas, and this lemma in the middle happens to be pushed. Then we get into a situation that looks like this, and now something interesting happened. We know that all of the lemmas here before hold if under the condition that this lemmas hold in the previous state. And now we see that every lemma that we have here also holds in the next state. Right? Which means if we continue this pushing process, now we'll be able to push all of those lemmas over here, because they depend only on themselves, and then push all of those lemmas here, here, and arbitrarily far in the future. And basically what it means is that the set of lemmas that we found here is an inductive invariant. So that's it. So that's how the algorithm is working. We're going backwards, computing predecessors using an SMT solver. Every time we stuck, we learn a fact, why did we get stuck? Whenever we've proven that for a certain bound the program is safe, we take all of our annotations and try to move them forward as much as possible. If at any point we have one time step where all of its annotations have been moved to the future, then we know that we found an inductive invariant and we stop. And if we didn't find an inductive invariant and we have to continue, then we take this bad state, we move it here, and now we look for longer counterexamples. But we keep all of the annotations that we have, which means we're never going to learn the same fact again and again. So just to tell you a little bit about Spacer. So it's actually used not just by our tool, so SeaHorn is sort of the main user, and that's why we created Spacer, but there's several other tools have been trying to use it as well. There's a version of SeaHorn called JHorn for Java. There's a pipeline built by NASA in order to verify Simulink code that goes into Spacer. I know that T2, which is a termination checker from Microsoft, started using Spacer for its reachability, and I'm now looking into how to do similar things, but for concurrent and distributed systems. Just to quickly argue that this not just works, but actually is sort of state of the art, what I'm going to show you is one slide from our results from the software verification competition, which is a place where tools like this compete on a common set of benchmarks and common missions. I'm just going to show you one set of results. So this is from a device driver category, which verifies Linux device drivers. What you're seeing here on this graph, each point here represents number of benchmarks solved at a particular time limit. Also, it's not really solved, but it's not really number of benchmarks, but the score, because you get more points for certain benchmarks than others. And this is where the SeaHorn line is. So the more to the right, it means the more benchmarks you can solve. And the only one that's better than SeaHorn is a tool that was specifically developed for this set of benchmarks. And this is the people who donated the benchmarks. So we're doing pretty well compared to state of the art. It's also been used in NASA just for a few small evaluations. So one of the interesting things that we've done is we've compared it with abstract interpretation for buffer overflows. And what we got was sort of expected, but we're really happy with that result, that the tool is much slower than an abstract interpreter in order to discover, say, all the buffer overflows, but it gives you a 100% guarantee. So with abstract interpreter, they could get to 90+ guarantee, or 90+% of buffer accesses were safe, whereas with SeaHorn, we can get to 100%. And of course, the interesting thing is how to combine the two tools, because obviously, if you can prove something with an abstract interpreter, you wouldn't then start proving it again with our tool. So to conclude, I've talked about SeaHorn. It is a state-of-the-art software model checker. It's based on an LLVM front end, which means that it can deal with actual C programs with arbitrary features in them, sometimes not very successful, but never because it cannot parse them or understand them. It's based on this idea of algorithmic logic-based verification, where we separate logic part of modeling or what we want to verify from the actual decision procedure. And it provides a framework to do research in this. Some of the things that we're interested to do in the future, so the counter examples, what I've showed you, we think that this would be a really useful feature to have for a tool like this. We're looking at concurrent distributed and embedded systems, and in particular in a cyber-physical domain. It seems like it's a very challenging area, but there's many interesting opportunities in there because people really care about making the systems work correctly. And there's a few works on extending what we're doing to richer properties. So recently we've tried to build a termination check on top of it. It's interesting to look at liveness properties, not just safety, and maybe use it for synthesis of things. That's it. Thank you.
Yeah. So one thing is, if you look at safety properties like overflows or division by zero or something like that, I have a problem with using LLVM and Clang, even front-end Clang and optimization in LLVM even more, actually look for that behavior and exploit it because it's like created as an optimizer, as a compiler. It's not for verification purposes. So if LLVM sees, oh yeah, this will be division by zero, it will replace that with something. And later you will say, oh yeah, that's no division by zero because you never saw it. It was just replaced. But if you maybe optimize it with a one later or you did something else, there is still this problem in there, but you just didn't see it because somebody removed it for you or hid it.
Right, and so there's always this question of where do you build your verifier? Do you build it at a very high level where you say I have the semantics of a programming language and I understand syntax and I do this? Or do you build it at a very low level where you say this is basically what's going to run? I don't care how it got there, this is what's going to run, this is what I want to understand. And we wanted specifically to do the tool that's close to the place where you run. And we're specifically interested in in properties which you can actually observe in the code that you run. And I know that for things like buffer overflow, it's a non-clear argument whether they should be checked at the higher level or at the lower level. And the way we were proceeding so far, we assumed that you first check them at the higher level, and then you have a gray area of things that you couldn't prove to be safe or not safe. And then for those ones, you go into lower level. And the reason for doing that is because verifying at a higher level is much, much harder. Because if you say that you're not going to allow to do any simplifications, any static reasoning, because you're so afraid of violating the semantics, then the reasoning gets to be really, really hard. And sometimes you can have a nice modular argument of why everything is okay, and then you should do it. But for things that you can't do that, at least you could go to lower level and see what you can do in there. But that's why for us it's really important, especially if we claim that something is wrong, to be able to exhibit it. Right? So at least we can say, I don't know what happened, whether in the previous talk we had examples where, say, a compiler would introduce an undefined behavior that will cause some sort of a bug. And what we want to do is say, if we claim that there is a bug, then you can actually observe it and then decide who's at fault.
Yes, some follow-up question. So LLVM has some rules, sanitizer tools that actually can provide C without undefined behavior. So this has as a result, you have a lot of function calls, a lot of runtime shading. Did you ever consider like having all this dynamic behavior? Would this make like your tool a lot less reliable, a lot slower in like giving results?
So we have considered, but we haven't done much, trying to use the tool to improve this, right? So you introduce dynamic checks in order to guarantee safety, but then you go static and you try to prove which of the checks you can remove. But we have not done that. You may be asking, if you code defensively and lots of extra checks, does it make a tool like that harder or easier? It depends, because sometimes you can use these annotations just where you can assume that they're true. For example, if in front of every access you check, if it's not null, then you can access, otherwise you go somewhere else. Then I can assume whenever you have an access that it is not null. And so I'll need to infer less facts about the program. But it does add more code, and so it's not clear. So we usually get this, for example, for buffer overflows, we need to instrument the program in order to make buffer overflows explicit. And then you run into a problem that sometimes an instrumentation that's good for runtime is very bad for verification. And so you may need a different instrumentation that plays well with the verification tool than the one that would play well with the runtime tool.
So let's take the rest of the discussion offline and have coffee instead. So thanks again, Arie.